So we are continuing with chapter 2. In chapter 2, we're going to look at two functions from algebra. They are the exponential and logarithmic functions. Okay? The exponential function and the logarithmic function. So why are they always together in the same chapter? It's because one is the inverse of the other. So first of all, let's identify them, and then I'll show you with the calculator in a minute why they even work on the same key in the graphing calculator. The exponential function is a base, which is a number. It's called exponential because the power is the variable. So f of x is an exponential function because the base is a number, and this is the variable. So possibilities here are 1/2 to the x, 2 to the x. Of course, they can be combinations, but I'm giving you just the basic functions. 3 to the x, I don't know, 1/4 to the x, 10 to the x, e to the x, and I can go on forever. Notice something very important. This base is here is 1/2, and then 2, and then 3, and then 1/4, and then 10, and then e. It's never 0, and it's never 1, and it's never a negative number. These are not allowed for a. A cannot be, the base cannot be 0, 1, or a negative number. And you can say, wait a minute, I know how to raise -2 to the 3rd power. I know how to raise 0 to the 4th. I know how to raise 1 to the 3rd. Yes. But if we use these as the base, then we will never be able to identify this function. This function will not exist if the base is 0, 1, or a negative number. So what can be the base? A number greater than 1, or a number less than 1 but positive. So again, a can be greater than 1, 2, 3, and so on, 1.5, or it can be between 0 and 1. It cannot be 0, it cannot be 1, and it cannot be a negative number. Now, these are very important exponential functions. They have a special name. This one is called common exponential function. And this one is called natural because it appears naturally. In other words, it appears in a lot of phenomena from nature. That's why it's called natural. And this is common. Base 10 is common exponential function. Base E is natural exponential function. So since I have the calculator here up, I'd like to show them here to you. So as you see, 10 to the x. So it's activated with the blue key, 10 to the x, I don't know, and I get 100. Or e to the x also in the background. It's not on the top of the key, but in the background, activated with the second key or the blue key, right? So e squared, let's say. What if I want e without a power? Then I will have to use the division symbol. It's right here in the background. So e, if you want to say, what is this e? Well, it's a very important number. It bears it. Why it's e and not a or b or c? Because it comes from Euler, the mathematician who established it. So it bears his name. So it's e, Euler's number. So it's 2.7182818 blah blah blah. It goes on forever. Okay? So e, this e is Euler's number. Euler's number. That's why it's e and not a or b or c or d or whatever else. Okay. So these are important because not because we have them in the graphing calculator, but they are important because the bases are special. They have special applicability, especially this one, Euler's number, the 2.7 yada yada yada. Okay, perfect. Moving on. Now I would like to talk about these, the log functions. However, I'd like us to graph. I would like us to discuss a graph with a base greater than 1, and also discuss a graph with a base less than 1. So here's how the graph looks like. And this is what we've been facing in the last 3 years. I never thought I would say that, but I said it. I have to. So for all bases greater than 1, it's a function that has a terrible growth rate. That's why they were saying, okay, 10 people get sick today, tomorrow 10,000 are sick. The next day 100,000 are sick. And that's why you've been hearing a lot by flattening the curve instead of just going like that, crazy. So flatten the curve. Let's deal with this pandemic, and you know what I mean. So this is f of x with a to the x for a greater than 1. It's an increasing function, terribly increasing, the fastest growth. Well, of course, the other one, the one with the base less than 1, it's still exponential, but the base is less than 1. So this one is always decreasing on its domain. This one is always increasing. So now I would like to discuss a little bit limits here. Yes, we are not ever going away or getting rid of limits. No, we can't. So now, can anyone tell us the limit of this function? I'm going to say is 10 to the x, let's say. 10 to the x as x approaches negative infinity, and also the limit of 10 to the x as x approaches infinity. By looking at the graph, can anyone specify these? It's okay if you're wrong, but from the graph, I'll take a sip of water. From the graph, will anyone tell us what is this limit and what is this limit?
The first one is 0 and the second one's infinity.
Absolutely. 0 and infinity. Whenever we determine the limit, now I can say it. I didn't say it last time when he talked about this, but I will say it now. Whenever we determine the limit either at infinity or negative infinity, and we get a number, not infinity, when we get a number, it means any number, including 0. It means, in this case, 0. Y equals 0 is a horizontal asymptote. What does that mean? It means that the function eventually approaches this number. Closer and closer, closer and closer. This is a horizontal line. It approaches a horizontal line. It will not cross it. It will approach it eventually. Closer and closer. So this is a horizontal asymptote. Now what about this? Can anyone tell us the limit from 1/2 to the x as x approaches negative infinity and as x approaches positive infinity? So I'm going to write them here.
0.
Yes. So as x approaches negative infinity, this is infinity, and the other one will be 0. So limit as x approaches infinity from 1/2 to the x, in case this is my 1/2 to the x, this will be 0. So now the horizontal asymptote for this one is at positive infinity only, and the horizontal asymptote for this one is at negative infinity only. Good. Any questions on this so far? On the refresher? Any questions? Okay, so now let's talk about the inverse function. So the exponential is the inverse of log. The log is the inverse of exponential. They have to have the same base. If they don't have the same base, they cannot be inverses of each other. If the base here is 2, the log has to have base 2. If base here is e, log has to have base e. Otherwise, they will not be inverses of each other. They have to have the same base. So let's talk about the exponential, the log and the graphs. So this is all algebra, refresher of algebra. We haven't touched on any calculus yet. Okay, so if we are looking at the common exponential, how do we write its inverse? We write log with no base, but we know the base is there. We don't write it though. It's faded, just for you to remember what it is. So if there is no base, it's base 10. How do we read this again? Log base 10 of x, which really we don't like. What we really like is common log x. But that's what it means. It means log base 10 of x. But we don't like to use this because we have a special name for it. And this is the common exponential. And this is the common log. Of course, the natural exponential has a specific inverse function, which is ln. You can say, why is it natural log? Why is it log natural? Because it comes from German. Okay? But it's natural log. So this is natural exponential. And this is natural log. So now I can show you again the graphing calculator. I have to share first. Okay. So here it is. Notice that 10 to the x shares the same key with log. These two are inverses of each other. 10 to the x and log. Meaning common log, common exponential. How do I find this? Okay, now I don't have to activate the second key. Log 7. And I get a number. Notice that these two are together on the same key. One in the background, the natural exponential, and the natural log, or if you want log natural, but it's natural log, is right here. So the same thing, natural log 7, of course. It's a different number. It's a different function. Okay. So before we graph, and I would like to graph them here together, can anyone give us the domain? So we carve the domain in stone. Let's carve the domain in stone for the exponential function. Yes. So the exponential function is friendly. Maybe I should not go back. I will write them again here. So the exponential function, this is how we like to write it. The exponential function is defined on all real numbers. So this is domain. And taking values, and this is the range, where? From these graphs, where is the range of the pure exponential function? Yes, the domain is all real numbers. And what about the range?
0 to infinity.
Awesome. Awesome. 0 to infinity. Excellent. We did not graph the log function yet, but it's the inverse function. I don't know how it looks like, but I know it's domain and range. Can anyone identify the domain and the range for the log function? You can say,
the negative infinity to infinity stuff.
say it again.
Would it still be negative infinity to infinity?
Okay, so let's think about it. This is a function, and this is its inverse. I'm sorry. This is a function, and this is domain, and this is range for the function. Now I want to determine the range, the domain and range for the inverse function. So the function takes x from the domain and makes it correspond to the y. What the inverse function does must take this y back where it came from. And this is the property of the inverse function. It's applied to this, returning back exactly where it came from. Not a different value, exactly where it came from. So now let's rethink the domain and range here.
Domain is 0 and negative infinity. And negative infinity to infinity.
Yes. So if this is negative infinity to infinity and this is 0 to infinity, the inverse function has to be applied to 0 to infinity and returning the values where they came from. That's the whole concept of inverse functions. So the exponential function is defined everywhere, friendly, I like to call it. I don't have to worry about it. Not friendly. Not friendly. Why? Look at this. I don't like this. Why I don't like it? Because I have to worry about it. Are there other functions that we worry about? Do we know other functions that we worry about that don't have domain all real numbers? They may, but in general, they don't. Not domain on negative infinity to infinity. Do we have three functions? Two that we worked with, and this is the next one. I don't like it. Do we have two other functions that we talked about from the beginning of the class that do not have domain all real numbers? We had both of them on the test, in which I said find the domain. Which two functions we found the domain, and it was not all real numbers?
Rational and radical.
Thank you very much. So any root with an even index, right? Because this quantity has to be greater than or equal to 0, and the rational function. So now this one joins the list of not friendly functions. This I have to worry about the domain, this I have to worry about the domain, this I have to worry about the domain. Okay, now I think we can graph them. So let me stop because I got to